Now it's wood. It wasn't. Okay. All right. So, well, that's not the hardest part of the lecture. So, okay, here we go. So now we're going to make C negative. See if your guess is coming true. So I'm making C a negative number. Now what's happening to my graph? It's moving down. So if I had, instead of x squared plus 3, I had x squared minus 3, notice my graph moves down 3 units. Okay? 3 units. I'm going to move this up so you can see it. So when you add and subtract a number from the original function, the original parent function, your graph shifts. Okay? So how are the inputs outputs of the parent function changing? So with this, we have with our j of x plus 3, we have added 3 to all of our outputs, or your y values, right? Your y values. So let's see what happens now. So in GeoGebra, we've graphed j of x and j of x plus 3 on the same set of axes. How are the two graphs related to each other? The graph of j of x has been shifted up 3 units. So the graph of j of x has shifted up 3 units, however you want to say it. Okay. So we say the graph of j of x plus 3 represents, because it's going up, a vertical shift of the graph y equals j of x up by 3 units. That's how we write it. Okay, everybody clear on that? It's going up, vertically up by 3 units. Okay. Okay, so what happens when you subtract a number other than 3? We've already looked at that with the slider. So here's now the general case. These are the types of things you put in on your cheat sheet for quizzes or tests. You want the general situation. So here's the graph of y equals some function. In our particular case, j of x is x squared, and we're adding c to it. Now remember, c is a variable, so it can be positive or negative. So the graph of y equals j of x plus c represents a vertical, because you're acting on the outside with the y values, a vertical shift of the graph j of x by c units, whatever c is. The shift is up if c is a positive number, and the shift is down when c is a negative. So it's very intuitive. Okay, vertical shifts up and down the y-axis is a very intuitive transformation. Okay, any questions on that before we move on? Okay, you're going to have lots of practice today once I go through these. Okay, so now we're going to look at horizontal shifts. So which directions are we going now? Instead of up and down? Left and right. So that's the language you'll want to use to talk about horizontal shifts. My function is moving left to right. Now remember, your function has not changed its shape at all, right? That y equals, that j of x, x squared function, when we moved it up and down, it kept all of its original shape, all of its original proportions. It was literally just plucking that parabola off and literally moving it, okay? So now which function are we dealing with? What's h of x look like? What's h of x look like? What's the parent function look like here? The absolute value of x, and what does that look like? Like a v, okay? So absolute value of x, just a v shape. So this is what absolute value of x looks like, okay? We know that on the right side, when x is 0 to infinity, it's just the line y equals x. It looks exactly like it did when it went in. When x is negative, it comes out to be positive, so it's the line y equals negative x. That's the definition of your absolute value. So let's see what happens now when I go inside the absolute value function, when I go inside and mess around with x. So now I'm not going to already perform the function and add or subtract something to it. I'm going to go inside and mess around with the input first. So let's mess around with the input and see what happens. Okay. So how are we messing around with the input now for this function? Excuse me, what would this look like? Excuse me. H of x says take the absolute value of x. So whatever the input is, you put right there in between absolute value. So what will this new equation look like, this transform equation? What will this look like? Not what happens to the graph, just what will the equation look like? Yeah, right. I'm taking the absolute value of x plus 3, okay? Because this is my input. Whatever's inside here goes into my function. So my input is x plus 3, and now I perform the absolute value. So changing the equation of h of x to h of x plus 3 is an inside change. We're now inside. All right, so we're doing an inside change versus an outside change. That is, we are changing the inputs or the x values of our function, not the outputs anymore. So here's a really important question. How are the inputs changing? How are the inputs changing? So how would you answer that? Well, here's my original input. Let's say we had -2, -1, 0, 1, 2. That's my original x. What's happening now to my, how are they changing? I'm not asking about the y's. I'm just saying, how are my inputs changing? Here are my original inputs. I'm adding 3 to them. So now my new inputs are x plus 3. So what would this first x value look like? Instead of -2, what would it now look like? I'm adding 3 to -2. Yeah, so what would it be? -2, add 3. +1. Okay. -1, add 3. Let's try that one. 2. 0, add 3. 3. 1, add 3. 2, add 3 is 5. Okay. So notice I've changed my inputs before I even go in and do an absolute value. Okay. So let's see what happens to the graph when I do that. And in fact, we could just kind of go back a little bit further here. We could go back, say, to -4 here. -4, -3, -2. So here's our x. Here's our x plus 3. -1, 0, 1. Okay. Let me put these in red. So here are our new inputs. What does, now let's go to the left here for a minute. What would h of x look like if I had my original outputs? What would h of x look like? If x is -4, what's h of x? 4, because I'm taking the absolute value. So I get 4, 3, 2, 1, 0, 1, 2, right? Now, let's see what it's going to look like. Here's h of x plus 3. So here's my original point. Here's my original point, -4, 4. So -4, 4, -4, 4. Here's my original point. -3, 3. Right, so far we're okay. -2, 2. So I'm just putting on some key points on my original on my original function, h of x. 1, 1, 2, 2, 3, 3, 4, 4. Okay. And now I'm messing around with my inputs. So now, when I was originally -4, I'm now going to be 3. I'm going to be moved 3 units, right? I'm now -1. So what's my h value? What's my h of x plus 3 going to give me? +1, 0, 1, 2, 3, 4, 5. Okay. So these are now my new points, -1, 1. So let's graph it. Well, let's have GeoGebra graph it. So your guess is, what does h of x plus 3 look like? See if you can figure it out before I make this slider go to 3. Well, it's always going to move over, but we have to use left or right. So you got to look at this. If you look at your points that we just did, you're going to get a sense of what happens. How did we get to 1 before? Well, anyway, we'll wait for a minute. So make a guess, and then you'll see. I'm going to make this go to 3 right away. Ready? Before, I had to be 0, right, to have my absolute value be 0, right? Now, x has been increased by 3. So in order to get 0, my x that I put in now has to decrease by 3, right? Negative 3 plus 3 gives me 0, and the absolute value of 0 is 0. So now our new function has these values. Negative 3, 0. Negative 2, 1. Negative 4, 1. So let's just compare those points. To go from 0, 0 to negative 3, 0, my graph moved, not over, left 3 units. For the same y value here I am 1 unit above the x-axis. And I was negative 1, 1 before. Now what am I? I'm 3 units smaller. I'm negative 4 and negative 2. That's what brings me 1 unit up. Why am I smaller? Because you added 3 to me. So I have to go 3 units to the left of where I was in order to come back to this same height to be at 1. So one way of thinking about this is, how do I get back to being x? How do I get back to x? So if you had x plus 3 and you wanted to get back to x, you would have to subtract 3. And that shows you left 3 units. You'd have to subtract 3 to get back to your original input. So it's a little counterintuitive. When you see x plus 3, you want to make that right, because anytime you think of plus, you think of the right. But when you mess around with the inside part of your function, it's counterintuitive. If you have x plus 3, all of your x values that you plug in have to be 3 units to the smaller to bring you back to the same height. So if we wanted to be a 2 now, say I wanted to get up here to the height of 2, I'd have to put a negative 5 in here, because negative 5 plus 3, the absolute value of negative 2 is 2. So because I'm adding 3, I have to shift everything to the right. So any shift, any value of c that's positive is a shift left. Okay. So now you say, okay, what happens when c is negative? I think you know your answer now. When c is negative, so now I'm looking at this. Suppose I looked at this, h of x take away 3. What would I have to add to x minus 3 to get back to x? What would I have to add to this expression to get back to my original x? 3. So because I'm adding 3, this is now going to shift to the right 3 units. There you go. There's h of x minus 3. It's totally counterintuitive. Anytime you act on the inside of a function, it's opposite of what you think. All right? So that's what you have to remember. So let's go down and fill this in. The graph of h of x plus 3 represents a horizontal, because you're working inside your function. So let's see here. Are we in the same place here? Right. So let's go back up here. How are the inputs, outputs of the parent function changing? The inputs have shifted to the left 3 units. So h of x plus 3 tells me I move to the left 3 units. So we move left 3 units. Okay. What happens when you add or subtract a number other than 3? Okay, so here's where we write our general case. This is what is good for your cheat sheet. So if the graph of y equals some function times x plus c, this represents, because you're working inside affects your x values. So just think on your graph, where are your x values? They're along your x-axis. It's got to be a horizontal shift. And it's going to be a horizontal shift of h of x by c units. Now here's the little counterintuitive parts. When c is a positive number, the shift is to the left. And when c is negative, less than 0, it's to the right. Okay, so that's your horizontal shifts. Okay. All right, we've got a couple more to do. We've got reflections. And reflections are mirror reflections. And we have 2 axes we can have a reflection over. Your x-axis or your y-axis, all right? So your x-axis or your y-axis. So what function are we playing around with now? G. Function G is the square root function. And let's take a look at what the square root function looks like. So here's your square root function. Here's G. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And it slowly starts to increase. It moves. The domain here is 0 to infinity, including 0. We can't take this even root or a square root of negative numbers. So our entire graph is on the right in the first quadrant, okay, when we graph it. So now we want to talk about what happens if we act on the outside of the function by just putting a -1 out there. So what's going to change when we act on the outside of the function? The y values or the x values? Okay, you don't know, right? So here's our original function right here, square root of x, right? So I could write that my new function looks like this, right? I'm just taking the opposite of g of x. Here's g of x. So have I already done the work and performed my function before I apply this? Right, so g of x has a value. I plug in 1, the square root of 1 is 1, and then what happens to that y value? It becomes negative. I put a 4 in here, I take the square root of 4, 2, and then I apply this to it. What does it become? Negative. So am I acting on the outside or the inside of the function? All right, are the outputs changing or the inputs changing? Outputs. So that's acting on the outside. Okay, so look, here's g of x. I've already performed the function. And now I'm going to take all those y values, all the outputs, and make them the opposite. So for exactly the same x value, I now am getting the opposite y value. Okay, so this function, oops, I guess I can't. Let's do it. Okay, there's the reflection right there. Okay, so my y values are now becoming their opposite. That's called a reflection around or across the x-axis. Some people say about the x-axis, some people say across the x-axis. It's like you have a mirror right here along the x-axis, and every single output here becomes the opposite. Okay. So let's go back to our sheet. Okay. So what are the equations? Y equals the opposite of g of x. What does that look like? If I now substitute in for g of x, what would that now look like? Go up and find g of x and substitute it. Negative square root of x, right. It's the negative square root versus the positive square root. Okay, so that's what y equals negative g of x looks like. And this is a reflection across the x-axis. because I've changed the outside or the outputs. Okay. So how are the outputs of the function changing? They are changing to their opposite, because that's what negative in front or -1 does. They are changing to their opposite values. So that's a reflection across the x-axis. You change your y values. So now here's g of x. G of x is square root of x, and now we're going to change it to become g of -x. So now it's going to look like this. I can't. I can't. I can if x is what kind of number? Negative number. So if I change the domain, I'm okay, right? If x is 0 to -infinity, I'm all set, right? I can take the square root of that. So I'm changing the inside of the function. I'm going to affect the inputs. All right. So let's see what happens. Here's G2. What is x? When x goes in as -1, we take the opposite of -1, we get 1. If we put x as -4, we take the opposite of the square root of -4, we get the opposite of -4, we get 4, we come up here to 2. Okay, so I had to change my domain. So this would be for on the domain negative infinity to 0. So if x is on that domain, if I put an x from here and I plug it in there, I'm all set. I can do it. So you just have to define the domain. So when you affect the inside part of a function, you have a reflection across your x-axis, your y-axis, okay? All right, so how are the inputs? The inputs have changed to their opposite. Okay, so in general, here's your cheat sheet information right here. The graph of y equals the opposite of g of x represents a reflection of your function over the x-axis. The graph of y equals g of -x, it represents a reflection over the graph over your y-axis. All right, so what I'd like you to do now, I want to take a little bit of a break, and I want you to go to your let's see, Smart Notebook, and move to, so I want you to try A, B, C, G, and H. So I want you, here's your parent function right here. It's a piecewise function. It looks like a squished up N. So here's the graph of f of x. I want you to match the pictures that go with A, B, C, G, and H at your tables. And you can talk to each other. You can work by yourself. Let me know if you need any help. I'll be glad to help you out. So let's take a look at this. So notice on my original function, I put some key points. Okay, my original function, I put some key points, right? And now all I have to do is look at my transformation and say, what happens to my output? What happens to my input? So here's A. A says, I'm changing my outputs by adding 2. So my entire graph is going to shift up 2 units. So I can take some key points. Here's a key point. 0, -2 is now going to shift up 2 units. So I find a graph that goes through the origin. So I can eliminate some of these. Well, this goes through the origin. This goes through the origin, right? So it's got to be one of these two graphs. Well, what else do I look for? Well, here's another key point. Pick any one. -2, 0, that my output's going to go up to. So when I go to -2, I should be at +2. So every single one of these points, -2, 2, -3, 3, they've all been moved up 2 points from the original spot. So this is A. Okay. Now, what are we looking for at B? B, you're inside the parentheses. This is a horizontal shift. It acts counterintuitively. Instead of when you see the +2, you are moving to the left 2 units. So that means all of these points are going to shift left 2 units. So take every single one of them and shift them left 2 units. Okay? Just shift them. Everything moves to the left 2 units. So it should look something like that without those little horizontal. So I just shifted it 2 units to the left. So now you've got to find that picture. And where is that picture? Right here, B. Everything has shifted left. This entire black function has just moved to the left. So this has shifted left 2 units. This has shifted up 2 units. Okay? Now this one, you're still acting on the inside. It's a horizontal change, but it's to the right 2 units. So now you look for your lowest point here to go to the right 2 units. So to find that function, you go down to here. This entire function is now shifted 2 units to the right. So this is C, shifted 2 units to the right. Okay. Now that takes care of those first 3. And now this says I'm taking all my outputs and I'm going to make them the opposite. So all of the points that are above the x-axis will now go below, and all the points below the x-axis will now go above. So this thing flips over the x-axis. And that picture is right here. This is G. That's a reflection across or about your x-axis. Okay. And then H says I'm a reflection across my y-axis. So everything that's on the right-hand side of this graph, this straight line, is now going to be a straight line on the right-hand side. It's going to be a decreasing line instead of an increasing. And this little like doodad here, this little mountain then going down, will now be on the right-hand side, and that occurs right here. This is H, a reflection across the y-axis. So those are your horizontal and vertical shifts and your reflections. So if you look at the activity, we have a few more situations to look at. We have a situation like E and F. E and F now, instead of adding, what are we doing? We're multiplying. So we're looking at factors of 2. That's the language we use. E has a factor of 2 because 2 is multiplying the function. In F, there's a factor of 2 affecting your x before you even get to operate on it. D is what we call a multiple shift, because D, we're doing a horizontal and a vertical. And here we have a double reflection, right? So let's take a look at when we have factors affecting our functions. So let's go back to our, where are we now? There we are. Okay. So vertical shrinks and vertical stretches, that's the language we use. We're going to stretch the function. So here's Liza, put your pen down. Okay, Liza's the parabola, and I'm going to stretch her way up like this. And then I'm going to make her really wide. Bend those elbows. There we go. So we're going to stretch Liza No, we're going to shrink her down. We're going to stretch her up. All right, how'd that feel, Liza? Pretty good? Okay, yeah. I know Liza needs to get a little more exercise, she tells me, so I just gave her you told me that, right? You like to get a little more exercise? Yeah, okay. All right. So what function are we operating on now again? The parabola is j of x, so what will y equal 2 times j of x look like? What will this look like? 2 what? 2x squared. There we go. So now we're looking at 2x squared. We're changing the outside of the function, of our parent function, because the parent function's already happened. X has been squared, and now I'm going to double all of the outputs. So we are changing the outputs. How are the outputs of the parent function changing? We are multiplying the outputs by 2. Okay. We are multiplying. So it's changing by a factor. That's the language we use. 2 is a factor because it's multiplying. Factor of 2. Okay, so in GeoGebra, graph j of x and then 2 times j of x on the same axes, and let's see how they're related. So let's go to GeoGebra and we'll look for our vertical stretches. That's not it. 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 Okay. Okay. I did by accident, huh? Open. Don't save. Vertical. Here we go. Okay. So here's our function, x squared. Here is our offspring. Notice when c is 1, it looks like exactly the same function. So you don't see another function. So what have we just changed c to? We've changed it to 2. So let's move c. Come on. Change it to 2. Ooh. Oh, why is this so nice stretch now? Feels good. So when we multiply the outputs, notice we're at exactly the same x values, right? For exactly the same x values, you're 2 times above higher because the y values are rising faster, aren't they, for the same x values? You're getting bigger quicker, right? They're rising more quickly. So when 2 is a positive number, this thing stretches vertically. So you've got to talk about which way are you stretching. Stretches vertically by a factor of 2. Factor is the important word here. Factor of 2. Factor of 2. If I make it 3, it's going to even get skinnier. Here's 3. Here's 2. Okay. So now what's going to happen, so this is when c is greater than 1. When c is a number greater than 1 out in front of your function, this thing stretches up. Right? Now, what's my only other choice? Well, I can make that number in front of x squared a fraction. So let's see what happens when c is a fraction. But before that, we do that, let's go back and fill in our notes. So in GeoGebra, we did this. How are the two graphs related to each other? J of x, the original function, is stretched vertically by a factor of 2. Okay. That's how I say it. Your book may say it a little different. So the graph of y equals 2 times j of x represents a vertical stretch by a factor of 2. You don't use the word units anymore. Units are just preserved for moving up and down and right and left. So notice, There's a big difference between this transformation and all the ones we've done so far, because now we've changed the shape of our original graph. Before, we were just moving it around, right? Like a little, like I pick you up and put you here, right? Now I'm changing the shape. So stretching and shrinking changes the shape of your original function. Okay, so let's see what would happen if we multiply by a number other than 2, which we already did. But let's see what happens when we multiply by a fraction. So let's see, where are my vertical? Nope. Wish these had little labels on them so I could find them. Okay, so now let's see be something between 0 and 1. So it's a fraction. Here's 1. It looks exactly the same as the parent function, x squared. Now what happens as I become a fraction? Whoa, wow, what happened? I multiply by 0, what does it become? The x-axis. Y equals 0 is the x-axis. So if I'm between 0 and 1, how is my shape change? Here's my original shape. What's happened? It's gotten wider, right? We say it shrunk. Why do we say it shrunk? Because now you're much closer to the x-axis than you were before. Your distances to the x-axis has gotten a lot shorter. It's rising more slowly. So we say that by looking at this following general cheat sheet statement. If you're acting outside the graph with a multiplier, C is a multiplier. It represents a vertical stretch or shrink of your original graph by a factor of C. When C is greater than 1, we get a stretch. And when C is between 0 and 1, when it's a fraction, we get a shrink. Okay. So again, your vertical stuff is acting just like you think. The big number makes it go up faster. The smaller number widens it out, right? So what do you think is going to happen when we look at the horizontal stretches and shrinks? So look here. Now we're inside. Yes, the opposite is going to happen. So here you always think, what are we working on? Ooh, now we're working on the step function. So the step function here is if you're a number between 0 and 3, you're the horizontal line, 3, y equals 3. And then if you're a number between 3 and 6, you're a decreasing line with slope of -1. So this is what you would look like. That's your step function. So between 0 and 3, you're the horizontal line 3, and then 3 to 6, you're a decreasing line with slope of -1. So, these horizontal things mess with your brain. So again, you look inside and you say, what would I have to do to 2x to get back Loretta, to get back 2x? Know that Beatles song? So what would you have to do to 2x to get back to x? What do you have to do to 2x to get back to x? Divide it by 2, right. Divide it by 2 is the same thing as multiplying by 1/2. Divide by 2, so you'd have to divide all of your x values by 2 or multiply by 1/2. So this means you're getting smaller. When you're inside, it acts differently than when you're on the outside. So changing the equation to k of times 2x works inside, and we are changing the inputs. And how are the inputs changing? So let's take a look. Let's make this value of C 2. So look at what's happened to your domain. Let's go back. When C is 1, what is the domain of our original function? What's the domain of K? 0 to 6, right? If I'm going to be shrinking this thing, I'm going to come in, you know, like those closing walls in those old horror movies, they start, you know, I used to watch, that's the kind of horror I had when I was a kid. They start coming in and they're going to, you know, crushing cars, right? So think about taking this thing and squishing it, dividing all your inputs by 2, making them half as small. Your domain has to decrease by a factor of 2. You divide your domain by 2. So here's my domain of K1. So I take 0 and divide it by 2, I get 0. I take 6 and I divide it by 2, I get 3. So my new function has to happen between 0 and 3. This whole thing has to happen in half of the distance from the y-axis. So let's see if it does. I got to change this. Okay, so there's your entire function. It's gotten squished. It's gotten closer. It's shrunk. It's much closer. If I took, look, this point now is 3, 0. What was it originally? 6, 0. So it's half as close to the y-axis as my original function, right? You can take any point. What was this point? This point was 3, 3. Now where is it? It's at 1.5, 3. So everything has scooted in half the distance from the y-axis. It's shrunk. All right. Now, where are we? How have the inputs of the parent function changed? The inputs are half of what they were originally, right? We've divided them by 2, or we've multiplied by a half, however you want to say that. So if you're ever interested in seeing how you put a step function into GeoGebra, this is K of X as a step function. Notice you put the piece of your domain first. X is greater than or equal to 0, less than 3, then you're the number 3. And if you're between 3 and 6, then you're this function, negative x plus 6. That's how you put a piecewise into GeoGebra. So when we multiply our inputs by 2, it represents a horizontal, not stretch, but shrink, because you're making this thing happen in half the time. You're running through this whole function in half the time you originally did, because you've sped everything up in the x value. If this was a time function, you're going the same distance in half the time, basically, if you think about it as a rate of speed. So the graph of y equals k of x has shrunk by a factor of 2. Okay, it's shrunk. Or you've divided it. Oh, excuse me, it's a factor of 1/2, sorry. Or you've divided it by 2. Okay, so it's shrunk by a factor of 1/2. That's the only tricky part. You've got to take that number and turn it into a fraction, because everything's half the size it originally was. So what happens now when we make C a fraction? Uh-oh, what do you think's going to happen when we make C a fraction? Let's see. So when the number's bigger than 1, it gets smaller and smaller and smaller. Now, what happens when I go the other way? I make it bigger and bigger. Let's go out here to, there we go. Woo! All right. There's 0. Okay, it's just going to be, so let's see, here we go. Let's go to half. Here's half. So if I make this K of 1/2 x, so now look at what the number is in front of x. It's 1/2. To get back to x, I have to double everything. Look at what's happened to my domain, folks. My domain starts at 0. How far out do I have to go to get this whole function in? To 12. I only had to go to 6 before, and now I've doubled. So now if I divide everything by 1/2, dividing by 1/2 is the same as multiplying by what number? 2. So when there's a fraction in front, it stretches. You go out twice as far. It takes you twice as long to get back to where you were. Okay? So here I was at 0. To get to 0 now, I have to go out 12 units because all of my x's have been multiplied by a half. So the graph of k times c of x represents a horizontal stretch or shrink by a factor of c. Or is it 1 over c? It's 1 over c. So when that's a whole number like 2, it's a stretch or a shrink by a half, right? In this case, it would be a shrink. If c is greater than 1, we get a shrink. And when c is less than 1, we get a stretch. Okay? So you only have a few minutes left. See if you can try the problems, the rest of the activity there. Here we go, right here. So you got D and E and F, and see if you can get L in. You only have a couple minutes, but do your best.